Okay, hello and welcome back. In this video, we're covering section 3.5 on various forms of writing equations of lines. So we'll see a couple different expressions of lines and how we can build them from various starting points. So the first version we'll look at is writing an equation in what's called standard form. And we've seen this a little bit previously, but just to write it out, if we want to write an equation in standard form, that is the form, and it's written generally as a times x plus b times y equals c. So notice the variables are on the left side. They have some number in front, and it's equal to some number on the right side. And a few extra details about this form. The numbers a and b aren't fractions. So they're integer coefficients. Also c as well. So they're not fractions or decimals. And usually a is a positive number. So if this ends up being some fraction, you could multiply everything by the denominator, and that would clear out the fraction. Or if a was negative, you could multiply everything by a negative, and that would turn at least the first term into a positive value. So let's practice putting things into standard form. Let's look at this first example. We have 3x plus 8 equals negative 2y. So I want to be in the form ax plus by equals c. I already have the x on the left side, so let's move this minus 2y over, and then we'll move the 8 over to the other side. So I will add the 2y to the right side, or to the left side, I mean. Well, we'll add it to both sides. That will move it from the right side to the left side. So it will appear as positive 2y on the left side. This will now be equal to 0. And then let's subtract the 8 over to the other side. So we'll end up with 3x plus 2y equals negative 8. Now it's in standard position. So let's try with the second example. Notice this time we're starting in slope-intercept form, which we've seen is a useful form if we're trying to graph a line. But we want to convert it into standard form. So let's get all of our variables on one side and then the constant number on the other side. So since the 3/4 is negative here, let's add it to the other side. So I'll end up, and I'll write the x term first. Positive 3 over 4, x plus y, because we had the y there already, equals 1 over 6. So we're almost there, but we don't want to have any fractions. So we want to multiply by the least common, it's actually essentially what would be the least common denominator, or the least common multiple of the two denominators that we have. So I know they both go into 12. 4 times 3 is 12, and 6 times 2 is 12. So let's multiply both sides by 12, which will result in multiplying every term by 12. So let's write that out first. So 12 times the first term plus 12 times the second term equals 12 times the 1 over 6. And we can view this as 12 over 1, and that can help see how this would reduce. Like 4 goes into 12 3 times, and 6 goes into 12 2 times. So that should leave us with 9x because the 3's will multiply now. 3 times 3. The y just picked up the 12 because it was like 1y originally. And then this will be equal to positive 2. So we got 2 times 1 on the right side. Now there's no fractions and the first term is positive. So in a lot of previous examples, we've started in standard form and then maybe converted to slope-intercept form in order to graph. This form can be useful too. It can be, sometimes it's easier to get the intercepts from something in this form because one of your terms gets deleted immediately if you plug in 0 for x or 0 for y. So it does have uses in other ways. All right, let's look at our next example. So this is writing the equation of a line given its slope and its y-intercept. And that already sounds like slope-intercept form. So we have our general slope-intercept form, y equals mx plus b. Let's remember what that looks like. So slope-intercept form, it's solved for y. Something is multiplied by x, m times x, and then we have some extra term, either added or subtracted. And this term is extremely useful because that number in front of x is the slope of the line. So we call that m. And b is the y component of the y-intercept. In other words, we would have some point 0, comma b, where b is the location where it passes the y-axis. So if you're given those two things as a starting point, it's really easy to build a line in slope-intercept form. So here they say we have a slope of -6, so that will be our b term, or our m term, I mean. And the y-intercept is the point 0, comma 5, so that 5 is the b term. So we know m equals -6 and 5 equals b. So we just need to plug that in to our form mx plus b. So I will substitute in -6 for m and +5 for b. So y equals -6x plus 5. So if you're already given the slope in the y-intercept, just want to plug into slope-intercept form. There's another very useful equation of a line called point-slope formula. And just like with slope-intercept, we have the slope and the intercept. With point-slope, if you know the slope in a single point, this time it doesn't have to be an intercept. You can plug it into this other formula, which they have written here. Y minus y1 equals m times x minus x1. And let me write that a little bit bigger down here. So this is called point-slope form. So y minus y1 equals m times x minus x1. And this is where m is still the slope. And x1, y1 is just some point on the line. And this is really just coming from our definition of slope. If you remember, slope we said was y2 minus y1 over x2 minus x1, or the change in y's over the change in x's. So let's just take y minus y1 and x minus x1. We still have our point y1 and x1, but we're leaving y and x here because we want to just create a general equation of a line. Well, if you multiply that whole denominator over, we just stick this in parentheses, multiply it to the other side, we'll have y minus y1 on one side, and I'm going to write that on the left side now. I'm just going to mirror image the equation. And then on the right side, we had m, and it's going to be multiplied by that denominator, x minus x1. So it's really just re-expressing that slope formula, the slope between two lines, and leaving one, the slope between 2 points, I mean, and leaving one point general and using the other point. So in this equation, you don't plug anything into that y or this x, just the m, the y1, and the x1. So let's see this example, and it'll make a little more sense. So we're given a line has a slope of -4, so I know that will be my m value. And the point 1, 5. So I can take the 1, I don't know why I wrote a minus here. That 1 is our x1, and the 5 is our y1. So just need to plug into the point slope form. So let me write it out again here. Y minus y1 equals m times x minus x1. So I'll plug in 5 for y1, so y minus 5. Our slope was -4, so I'll put that in. And then x minus 1. 1 was our x1. So notice we're keeping this x, or this y and this x in the equation, and plugging in everything else. Now this question wanted the final line expressed in standard form. So let's clean this up and get our x's and y's over to one side and everything else over to the other side. We'll start by distributing this -4 through to both terms. So y minus 5 will equal -4x, and then -4 times -1, we'll turn that into a +4. Now I have the y on the left side already. Let's add the 4x over to the other side. I'll stick that in front. So +4x plus y minus 5 equals 4. Now let's just add that 5 over to the other side. So 4x plus y equals +9. 4 plus 5. Now we're in standard form. X and y is on the left side. There's no fractions, and the first term is positive. So point slope form is extremely useful when you know a single point and then the slope of the line. And then usually after you plug into point slope form, usually want to convert it to some other form. So either standard form, or we could have converted it to slope intercept form as well. So that's if we're given the slope of a line and a single point. But let's say you're just given 2 points on a line. So that's our next example. We can still use point slope form. We just need to find the slope between the 2 points as our starting point. So that's the little instructions they give us. If we're given 2 points on the line, first use the 2 points to find the slope, and then use the slope and either one of the points. It doesn't really matter. As long as we stick with a single point, you can plug that into point slope form. So let's give that a try. So here we need the equation of a line given these 2 points. Our first point, I'll just call it P1, is 4, 9. And our second point, we'll call P2, is 2, 6. So first, let's find the slope between these 2 points. We'll call that step 1. So find slope between the 2 points. So that's our slope equation, y2 minus y1 over x2 minus x1. So from P2, y2 would be 6, y1 would be 9 from the first point. So difference of the y's over difference of the x's. In our second point, we have 2 as our x value. In our first point, we have 4. 6 minus 9 gives us negative 3. And 2 minus 4 gives us a negative 2. Then since both the numerator and the denominator are negative, that'll cancel out. We'll just get 3 over 2. It'll turn positive. So that's our slope. Now we can take this as our m value and pick its second point. Just pick one of these 2 points and plug into point slope form. So that will be step 2. So use the slope from step 1 and 1 point. So I'm going to just pick this first point, but this would work out if we pick the second point as well. So let's take our m value as 3 over 2, and our point will be 4, 9. So we'll plug into point slope form. So I'll write that out just to remember. That's y minus y1 equals m times x minus x1. So this will be our x1, our y1, and we have m. So let's plug in. So we have y minus 9 equals 3 over 2 times x minus 4. And notice in the question, they want us to express the answer in slope-intercept form. So slope-intercept form is y equals mx plus b. It's solved for y. Everything else is over on the other side. So first here, you'll typically want to distribute this term through the parentheses and then move the other term on the other side over. So we'll have y minus 9. This will just give us 3 over 2 times x. And then we're going to be, we have our minus, and we'll have 3 over 2 times 4. I'm going to write that as 4 over 1. So that looks like this 2 will go into the 4 2 times. So that should give us a negative 6 overall. Let's write that out. Y minus 9 equals 3 over 2x minus 6. Now we just need to add the 9 over. Let's jump over here. So y will equal 3 over 2x. We have 9 minus 6. Yeah, so that will be positive 3. Now we're in slope-intercept form. So we've seen a few different starting points. In the second example, we were given the slope and the y-intercept, and that's easy just to plug into slope-intercept form. From example 3, we were given the slope as well, but also just a single point, so no longer the y-intercept, just some other point on the line. And that's where point slope was very useful. Or we could just be given two random points on the line. Then here we have to first find the slope using these 2 points and then plug into point slope form. So a little extra step there. So these have all been equations of slanted lines, but we also have horizontal and vertical lines as well. And their equations have a special kind of form. So our clip from the textbook says that the equation of a horizontal line containing some point will just be y equals whatever the y part of that coordinate point is equal to. So let's think about how this can make sense. Well, let's just look at this first example. It says write an equation of the horizontal line containing the point 7, comma, -1. Well, if this is a horizontal line, it looks something like this. Let's go out to 7, 2, 3, 4, 5, 6, 7, and -1 is down here. So imagine some horizontal line going through this point. Let's make it a little brighter. So it also goes through -1 on the y-axis. So any point on this line will have this y-coordinate of -1. Say like the intercept over here would be 0, -1. This was our point 7, -1. Or we could go over here. This looks like it would be 3, -1. So x can be anything. It doesn't really matter what x is. Y will always be equal to -1. So that's how we describe the formula. We can just say y will always equal -1. And in this case, it doesn't even matter what x is, so x doesn't show up in the formula at all. And we would see this result as well if we took the previous approach. If you remember, the slope of a horizontal line is equal to 0. And in fact, let's do that just to see. Let's plug into point slope form where the slope is equal to 0, and that's our point. So we would have y minus y1, y minus -1 equals m, so that's 0, times x minus x1, x minus 7. Notice the 0 is just going to delete this term on the right, so this will give us y plus 1 equals 0, and then we can subtract the 1 over, y equals -1. So we would see a similar thing if we had a vertical line. Vertical lines look like x equals something. We can make a similar argument. We could say some vertical line will always have some x value. The x value will be the same for every coordinate point. And then the y value can be anything. So similar setup there. So that gives us a handful of techniques for writing equations of lines. So just to summarize these again, if you're given the slope and the y-intercept, use slope-intercept form. If you're given the slope and a point on the line, then you can use point slope. If you're given 2 points, then use the slope and either one of the points. So you have to first find the slope. So find the slope of the line, then use the slope in one of the points in point slope form. And then if you're told the line is horizontal, you can just say y equals that y component, or if it's a vertical line, it'll just be x equals whatever the x value in your coordinate is. So we have a handful of techniques now for creating equations of lines. If we know it's the line's relationship to another line, that can also be helpful in creating the equation of a line. So this is where we'll see if a line is parallel or perpendicular to a given line. And if you recall from a previous video, parallel lines would look something like this. And the key attribute of parallel lines is that they have the same slope. So if you know that our line is parallel to some line, it will have the exact same slope. The y-intercept will be different, but the slope will be the same. And then if two lines are perpendicular to each other, so they have a right angle, they meet at 90 degrees. Remember, perpendicular lines their slopes are negative reciprocals of each other. And I'll give an example. So if one slope is 3 over 4, then the perpendicular slope would be negative 4 over 3. So the sign goes from positive to negative, and the fraction flips. If this was already negative, if it was negative 3 over 4, then this would be a positive 4 over 3. So it doesn't always go from positive to negative. If it's already negative, it'll become positive. The main thing is that the sign of the slope switches, and then the fraction flips. That's what they mean by negative reciprocal. Oops. So let's see a couple of examples here. Oh, looks like I need to erase a little bit. All right, sorry, 1 second. Just cleaning up our second example. Okay. All right, let's look at this first one. So we're given we want to create a line that contains the point 2 comma negative 2, and we're parallel to this other line. So I'll write that we're parallel to this line, y equals 1/2 x plus 1. So that means we're going to have the same slope as this line. We can just steal it from this line, basically. I know that m is going to equal positive 1/2. So now we have our slope and a single point on the line. So let's use point slope form. That was y minus y1 equals m times x minus x1. Again, where m is our slope and x1, y1 is some point. And those are the two things we have here. So let's just plug into the formula. This would be y minus negative 2 equals 1/2 times x minus 2. So plugging in all our information. That minus negative will become a plus 2. And we want the final equation in slope-intercept form. So let's distribute this 1/2 to both terms. So that will become 1/2 x. And then 1/2 times negative 2, that would just cancel to negative 1. So 1/2 x minus 1. Now let's just subtract that 2 over. So this should become y equals 1/2 x. Negative 1 minus 2 will be negative 3. So we have our line in slope-intercept form. So if you're parallel to some line, you can just steal the slope from that line. It'll be the same. Let's look at a perpendicular example. So now we're told that we have a point negative 4, 3. And this time we are perpendicular to another line. And they give us a line in standard form, 3x minus 4y equals 8. So we know we're perpendicular to this line, which means we will have a negative reciprocal slope, but it's hard to read the slope when it's in standard form like this. So first let's convert this over to slope-intercept form. Let's solve it for y. So let's first subtract this 3x over to the other side. So I'll be left with minus 4y on the left side. Then I'm going to write the x term first. It'll be minus 3x because we subtracted, and then we have a positive 8. And then let's divide everything by this negative 4. So we'll be left with y on the left side. This will become positive 3 over 4 because we have a negative divided by a negative. And then 8 divided by negative 4 will be negative 2. So I'm less interested in this number and more just in the slope of this line. So this line has a slope of 3 over 4. So that means our slope will be the negative reciprocal. So it's positive, so it's going to become negative. And instead of 3 over 4, I'll say 4 over 3. So negative reciprocal. Now we know our slope and a point on the line. So let's plug in, I'll write out point slope form again. Y minus y1 equals m times x minus x1. So plugging in all of our information, this will become y minus 3 equals negative 4/3 times x minus negative 4. Have to be careful with the double negatives. And this wants the equation in standard form. It says find the standard form for the equation. So we want our x's and y's on one side and without any fractions or anything. So first let me get rid of the double negative before I end up losing track of that. So this will be negative 4/3 times x plus 4. So I think I'm going to already multiply everything by this denominator, by this 3, so that we won't have any fractions to start with. Because that was one condition for standard form. We didn't want any fractions. They always had, we want to have integer coefficients. That would be another way of saying that. So let's multiply both sides by 3. Imagine multiplying the left side. And then we'll also multiply the right side by positive 3. So on the left side, let's distribute that through. That'll become 3y minus 9. And then on the right side, this 3 will cancel with the 3 in the denominator, because this is like a 3 over 1. And that's what we want. It's going to clear out that fraction. We'll just be left with negative 4 times x plus 4. So the 3 wouldn't multiply by anything inside, just the coefficient in the front. Now let's distribute that negative 4 and then put it into standard form. So we've got 3y minus 9 equals negative 4x minus 16. Now I will add the 4x over to the other side, so it will appear as a positive on the left side. So 4x plus 3y minus 9 equals negative 16. And then let's add the 9 over to the other side. So on the left side will be 4x plus 3y. And then on the right side we have negative 16 plus 9. So that should give you negative 7. So now we are in standard form. No fractions, and the leading term is positive. And our x's and y's are on the same side. So you may be given a line that it's less easy to just read the slope off of if it's not already in slope-intercept form. So you might have to do that first in order to determine what your slope should be. And then from there, you can plug into point slope form and then put it in whichever particular form they're looking for. So just make a note of the question. In this case, it said to put it into standard form. All right, let's look at an application problem. This is using some real-world data. So let's read through this example. It says, since 2005, vehicle consumption of E85 fuel, that's ethanol 85%, has increased by about 8,260.7 thousand gallons per year. So kind of a strange way to give the unit. It's saying 8,000 thousand. So it makes the number kind of look smaller than it is. It's actually quite big. In 2009, approximately 70,916 thousand gallons were used. So it wants us to write a linear equation to model this data and to let x represent the number of years after 2005. So I'll make a special note of that. We want x to represent number of years after 2005, and y is the amount of fuel in thousands of gallons. So if we need to create the equation of a line, we typically need the slope of the line and then some point on the line. So how can we find the slope? Well, notice this language. It says the amount of fuel has increased by this amount per year. So it's a rate of change. That's actually what a slope describes, like how the line is changing. If we have a positive slope, it's some increase, amount increase over some given period of time. If it's a negative slope, that's something is decreasing over time. If it's a very high slanted slope, a very large value, it's increasing very quickly. Whereas if the slope is maybe a small number, more flat, it's more of a slow, gradual increase over time. So the slope of a line, you can view it as a rate of change, as a way of measuring how much it's changing over time. So when we're given that statement, it says it's increased by 8260.7 thousand gallons per year. And we know that x is time and y is in thousands of gallons. This will be the slope of our line. Per year will be per unit, per x unit. So we can say m will equal this number, 8260.7. And then they give us a specific value on a specific date. They said earlier in 2009, 70,916.6 thousand gallons were used. So that is actually giving us another point on the line. In 2009, since X is number of years after 2005, that would be 4 years after. So that would be an X value of 4. And then the amount of gallons used, that's our Y value. That's the 70916.6. So now we have the slope of the line and a single point. We can just plug into point slope form to build the equation of our line. So let's do that. Oops. So remember, point slope is y minus y1 equals m times x minus x1. So let's plug in our values. Y1 is this large number, 70916.6. M is 8260.7. And x1 is 4. So let's put it into slope-intercept form. It's usually very useful. So first, let's distribute this large number through to both terms. So we'll have y minus 70916.6 equals 8260.7x. And then if you multiply this number by -4, you should get negative 33042.8. Now we just want to, oh, and this should be a minus. I wrote a equal sign there. Now we just want to add this term over to the other side. It will add to the term that we just created. So we'll be left with y on the left side. We'll have the 8260.7x. And then this essentially becomes 70916.6 minus 33042.8. So that will give you a positive 37873.8. So that's the equation of a line that will now model this situation that we have, this increase of gas consumption per year. Now we can plug in any x value, where x is some number of years after 2005, and get at least an estimate for how much gas will be produced in that year. So that's what part B asks us to do. It says how much did they use in 2005 and how much was used in 2007. So let's look at those two. Let's keep our equation here because we'll need it. So in 2005, well, we said x was years after 2005. So that means x equals 0. This will actually be our y-intercept. You can imagine plugging in 0 for x, we'll just get this term since it's in slope-intercept form. So we can say it would be 37873.8 thousand gallons. That's how much was used in 2005. And the second part asks for 2007. So that was 2 years after 2005. So that means x will equal 2. So let's just plug it into our equation. This is now a mathematical model that will give us some useful information. So plug in 2 for x. So if you calculate this out, take 8260.7 times 2 and then add 37873.8. That should give you 54395.2, and this will be in thousands of gallons. So it has increased in 2 years, and we're predicting it will increase from there. So this is an example of creating an equation of a line given some data about a system or about something happening in the world. You can create an equation which then can be used to predict output values at some other points in time. So pretty good use of the equation of a line. All right, that's it for this section. So we looked at writing the equation of a line in standard form. So that was ax plus by equals c. We wrote the equation of a line given its slope and y-intercept. And that was using slope-intercept form, y equals mx plus b. We wrote, using point slope formula, the equation of a line given a slope and a point on a line. So point slope was y minus y1 equals m times x minus x1. And then we use that same formula when we're just given 2 points. We had to just first find the slope between those 2 points. We saw the equation of horizontal and vertical lines, and how to write an equation for a line that's parallel or perpendicular to another line, and we just finished off using some real-world data to write a linear equation. Okay, that's all for this video, and I'll see you next time.